Then you guys will, in a week, you'll find out whether you're coming back or whether you guys are out in the workforce. Okay, I have a message here from Tessa. Just read that. Tessa, doesn't really make any difference. You're gonna when you're making up these 1,200 grams of aggregates for an actual mix design, you're gonna dry it again. You're gonna put it on a hot plate, and you're gonna dry it, and then you're gonna get an additional mass. Because when you put these aggregates together, you may not get at them, say, for a week or so. And if they're in a bag, they shouldn't take on moisture. But you got to heat your aggregates anyways when you're adding your hot AC to it. So you're going to get another final mass. And you're going to find out that you may have made up samples of 1,200 grams, but in actuality, you may have less than 1,200. You may have a little bit more than 1,200. Because when you're weighing these up, and you're always rounding up and up, 1,200 is roughly the amount of aggregate you need. Because we know then that we'll get the proper volume of briquette. Okay, if you're watching me, I'll get a proper volume of briquette, diameter, and height. I'm going to try and go over in the lab portion, over the video that Ray put together. And we'll go through it. We'll stop at the highlights. But I'd like to review that video on Marshall Mix Design, compacting of the briquettes, the testing for specific gravity, for maximum theoretical specific gravity, and so forth. If you round up to the nearest gram and you get like 1,201 or 1,202 for this lab for today that you're submitting, that's fine. Is that answer, Tessa? Yeah, okay, good. Okay, why don't we get started here? We want to cover the hot mix asphaltic properties. What you're doing here is you're putting together aggregate. For the lab that you're just submitting, you blended it physically. In other words, you did a combined gradation, theoretically. You separated it. Each material you separated it into the appropriate fractions that are recommended for the mix design. You weighed out that aggregate. You combined it all. And now, if you went and sieved that aggregate, you should get what your theoretical shows, your blend. Your blend should be the blended aggregate that you did in lab 6. And with that is where you would have 4 or 5 samples made up. 3 of the samples, you would add the AC to it to compact the briquettes. And these briquettes are used to determine the specific gravity of the mix, to determine the maximum theoretical specific gravity. That would be the 2 samples that aren't compacted. And then you would take an average of it. So we'll go over that in the lab. But right now, what I'd like to do is cover the properties and the benefits. And what. Okay, so give me a minute here, and I'll put something on share, but I'm going to record first. Here. Okay, we're recording. And let me just put up a share here. Okay. Everybody see that okay? Okay. Hot mix asphalt volumetric properties. By doing this Marshall mix design, we're going to be able to determine a job mix formula or a mix design. In asphalt, asphalt, we talk about job mix formula. It's technically a mixed design, just like you'd have in concrete, except it's for asphaltic concrete. Okay, so from these tests that we're going to run, you can then do a void analysis. You can do stability analysis, flow analysis. And from that, we're going to pick an optimum AC content that all the properties meets the design, which technically is meeting the city of Winnipeg, excuse me, specifications. So this is what we're all about. And when you do an asphalt mix design, you compact briquettes, we'll look at that in the lab, at various AC contents. And because technically in your group, we have like 6 lab groups, we would do one at 4%, 4.5, 5, 5.5, 6, 6.5. And for each one of those, you would compact 3 briquettes. And you would do probably 2 samples of the AC and aggregate mixed together loosely to determine the maximum theoretical specific gravity, or GMM, as it's the acronym is noted for. Okay. From that, we plot the results, and we'll look at that later. There's 5 or 6 graphs that we put together, and from that, you're going to choose at what AC everything else makes it. Okay. Terms: bulk specific gravity of the compacted hot mix asphaltic concrete. GMB, G stands for specific gravity, M stands for mix, B is your bulk. Okay. GMM, maximum specific gravity. G, mix, maximum. Air voids. V, subscript A. Effective specific gravity of the aggregate. That's the aggregate volume that absorbs the asphalt. Specific gravity G, S for aggregate, call it stone if you want, sand, and E for effective. Most technical publications use these acronyms. I use them. The Asphalt Institute uses them. If you see a lot of YouTube videos, or you may see some other papers that are written, people use a different acronym. I know even MI would use totally different, but I'm trying to be universal. So what the majority use. VMA, voids in mineral aggregate. And the voids filled with asphalt cement. Voids filled asphalt. Okay. That may also be known, and we'll look at that later, VBE, the volume of bitumen effective. Okay. What the effective asphalt content is, it's the asphalt that is filling the voids, coating the aggregates. It's effective. Part of your total AC that you add to the aggregates gets absorbed. Okay. PBA, percent bitumen absorbed, and we'll look at this. Any questions so far? Well, as with aggregates, it's the specific gravities that define the relationships between mass and volume. And that, therefore, air voids, VMA, voids filled with asphalt, and so forth. Okay, so these are terms. These are also explained on your sheet here, a representation. So you can see here again, you've got a hot mix asphalt, comprises of air voids, and it's comprised of aggregates, and it's comprised of asphalt cement. So if you look at here, if you've got aggregate VSB, the volume, bulk volume of the stone, plus the air voids, gives you the total volume, VMB. Now, the voids in mineral aggregate, there's some air voids in it, and there's the voids filled with asphalt, sometimes referred to and is also referred to as VBE, the volume of effective bitumen, VBE. It's the same thing. VFA, VBE, just a different term, but it's the effective bitumen, AC, asphalt cement. Another name for asphalt cement is bitumen. And you can see that part of this aggregate has some absorbed asphalt. A certain percentage of that aggregate absorbs the asphalt, just as the aggregate absorbed concrete water in a Portland cement mix. VBA, volume bitumen absorbed. The aggregate that does not have AC absorbed, it's the effective volume of stone effective. You can see here on this diagram, we can have mass on this side and we're going to have volumes on this side, or flip them over. It's very similar to the three-phase diagrams you guys took in Geotechnical Materials 1 when you were calculating volume mass density relationships. Essentially, that's what we're doing here, except we have ingredients are different. Down here, you can see that I've got the VMB and what it stands for. I got the acronym and I've got its definition. Know this chart, print this chart, have it ready for yourself. You can calculate all the volumetric parameters off this chart, or you can use the formulas with a little bit of interpretation. Mass determinations are usually simple. Okay? You place something on a scale and you weigh it. Think of the basic phase diagram as an empty bucket. First thing you add to the bucket is aggregate. You've got aggregate and air voids. Okay, volume of solid particles, volume of voids that can get filled with water, or they can also get filled with AC. If you add the cement to it, the asphalt cement, some of the voids are still going to be present, air voids. Some of that AC is going to coat the aggregates. And with time, some of that AC gets absorbed into the aggregate, into the pores of the aggregate. Because the aggregate has surface voids, some of the asphalt fills a portion of these voids. The remainder of the asphalt remains on the surface of the aggregate. This is the asphalt that is available for sticking the aggregate together and is referred to as the effective asphalt content. Okay? VFA or VBE, effective. When the sample is compacted, the total volume will also contain a percentage of air voids. VMA is the sum of the air voids and the volume of the effective asphalt. So the VMA is basically made up of two things, AC and air voids. Because we don't fill, you don't want to have zero air voids. You'll have excessive bleeding. And you may have seen that sometimes when you're driving down a highway, on say on a hot mix pavement or asphalt roadway. You'll be driving along, and all of a sudden you're looking ahead and you can see kind of like a slick. It almost looks like there's water sitting on the road. And as you get closer, it's not water, but it's a richer area of AC. So if something happened in that area, either the AC content went up, it started to flush out, or there could have been something wrong with the air voids, the compaction. But that's bleeding. You're getting excess AC coming to the surface. Okay? So that's called bleeding. Any questions so far? Okay, let's look at the mix. Basically, it's asphalt and aggregates, right? AC cement, and you compact it. So if you looked at a sketch here, you can see that you've got aggregates, you've got a film of AC around it, and you've got air voids. So essentially, if you knew the mass of the aggregate and you knew the mass of the AC, and you knew specific gravities of the aggregate, you knew specific gravity of the AC, you can calculate the bulk specific gravity. Okay, it's mass over volume. Typically, because this is specific gravity, you should be multiplying the volume by the density, 1,000, or 1 gram per cubic centimeter. So technically, this is mass over volume, kilograms over cubic meters. That's not specific gravity, that's density. Okay, so these formulas here you'll see should be multiplied by 1 gram per cubic centimeter, or 1,000 on the bottom end. Okay. But if you're working on units of 1, you just drop the units and you've got it. Testing again. There's your briquette that you compact in the Marshall. If any of you guys witnessed or watched that video that's been uploaded in the lab and in the lecture here, you'll have seen that Ray was compacting a briquette. So these are what we refer to as the asphalt briquettes. It's aggregate. This is what is made up of your 1,200 grams of aggregate, plus if you're batching at 4%, you're going to determine what's my AC content in mass that is 4% of the total mix. Okay, we'll go through it. So you're going to get an SSD. Here's the formula. And when we look into our labs, you'll see these on your the labs that you're going to be doing for this week. Okay, MTD. This is a mix. That briquette that we just looked at, if it had no voids in it, all it had was aggregate and AC. You'd have no air voids. This is what you'd have. You've got aggregate, AC around it, compacted. So keep in mind, your GMM is the maximum theoretical specific gravity, right? It's greater than GMB, but the volume, VMM, is less than VBM because there's no air voids. You've taken that AC and you've taken that aggregate and you've compacted it in such a way that there's no air voids. So your volume is less. Keep that in mind. GMM, maximum theoretical specific gravity of the mix. And here you can see it's just the aggregate in AC divided by the volume of aggregate in AC. Whereas before, we had volume of aggregate, volume of AC, plus volume of air voids. There's the difference. Okay. And again, it tells you how you do the test. You would compact 3 briquettes, so you can get an average of them. You would mix up 2 samples. And when you're doing specific gravity, maximum theoretical specific gravity, you try and do it at the AC content that your mix design is going to be at. So say 5.3, and you know that from experience. So when you're doing this, you would try and run a specific gravity on a mix at the optimum AC content. But you can run that on any AC, it doesn't matter. But it won't change. If you do it at 1, it should be the same for everything. So here's a loose mix. And here you can see you spread this asphalt out. It was hot, but you spread it out and as it would cool, and then you break it apart, and you want it to be free flowing. In other words, you want the aggregate to be coated, but individually. So you can get it into a flask, or you can get it into the bowl when you're doing the MTD on it. And here is where you would do. You would take that mix and you would dump it in here, put it on a vacuum with water, and we'll look into that when we do the asphalt. Sorry, when we do the lab. Okay, this tells you the calculations. Again, it's just the dry mass divided by the mass of dry sample minus the mass of the sample in water. We're doing volume displacement. That's what it is, mass over volume. Percent air voids. Now we're getting into how we calculate these. We know we need to have air voids. And here's where you can say, this in fact is GMM, okay, divided by GMM minus GMB over GMM, so it's 1. And you can see here that if you cross multiply, you're going to be left with the volume of aggregate and AC divided by the volume of aggregate, the AC, and the air voids. So this is just tells you how they came up with the formula. An example, I'm not going to go through. Okay, this is the effect of specific gravity. So far, so good, guys? This is going to lead up to when we get into calculations. I've already uploaded, and some of you may or may not have done it, but that assignment's been uploaded for quite a while on calculating air void or volumetric properties of an AC mix. Those are typical type of questions that you're going to have on a quiz, you're going to have on an exam, and you're going to be expected to calculate. So I'm hoping you guys have looked at it already, or you will be. If we look at a solid particle of aggregate, you can see we got voids. The effective specific gravity of the aggregate consists of the dry aggregate. And you divide it by the effective volume. Well, what is its effective volume? It's the volume of the solid particle and the volume of the surface voids that aren't filled with asphalt. See these voids here in black? Doesn't include them, but it includes the blue. That's the effective. So now you can see the volume here would be different because you're not including the AC. So these are permeable voids not filled with asphalt. So the GSE, effective specific gravity, is the dry mass divided by the effective volume, which is the volume of the solid particles, plus the voids filled with water, but not voids filled with asphalt. Okay. Again, that's how you calculate. Now remember, specific gravities are aggregate properties. GSE, stone. Not GMB, because GMB would be the bulk specific gravity of the mix, which would include everything. So GSE is an aggregate property. And there's your formula there. PB would be the percent of bitumen. So in other words, if your mix design calls for 5.4% AC, it'd be 100 minus 5.4 PB. Does anybody know what GB stands for? Anybody? Hello? You're sleeping? Blurt it out. Yell it out, guys. Can everybody hear me okay? G stands for specific gravity. What is the B?
Maybe bitumen?
Bitumen, right. Exactly. Remember I said PB is the percent of bitumen. GB is its specific gravity. And we know that AC runs 1.029, 1.03, 1.025 in that range. I've seen them even as high as 1.04. Again, depending on whether you're using 150, 200 pen grade, or you might be using 100, 200 pen grade, whatever the case may be. So GB is the specific gravity of the bitumen. PB is the percent. Remember, percent bitumen is based on total mix. Okay. Make sense? Here's an example. I'm not going to go through it, but here's this one's based on 5%. And there you see your GB 1.03, 5% is your percent bitumen or percent AC, and you've got an effective specific gravity of 2.70. Voids and mineral aggregate. Okay. This is a percent of total mix. Okay. And the city of Winnipeg, I think we're going to be shooting for 14 and a half voids and mineral aggregate. It's a percent of total mix. Now, there again is the formula, pretty straightforward. Bulk specific gravity of the mix times the percent stone. If you got a 5% AC content, what's the percent of your stone? Anybody? You've got a mix. 5% of total mix is AC. What's your percent aggregate? PS. Anybody? You've got a mix. 100% total mix. 5% of that total mix is AC. $95. 100 minus 5. Anyhow, PS 95. Remember, our example had 5% AC. So you got a VMA of 13.7%. Voids filled with asphalt. Now, the voids filled with asphalt is a percent of the VMA, not of the total mix. Okay, you've got VMA, which is your voids and mineral aggregate. There's some AC in there. Okay, the voids filled with asphalt, or the effective asphalt. So what percent of the VMA is filled with asphalt? VFA. Well, it's a percent of the VMA. So here you can see it's the VMA minus the air voids divided by VMA. Pretty straightforward. And VFA is going to be what it's going to be based on the VMA, based on the air voids. So you'll always notice there's really no specification for void filled with asphalt. There's specifications for VMA, specifications for air voids, specification for AC. So it's just a function of it. It is what it is. It's going to be whatever it is. It's a mathematical function. So it's a percent of the VMA that is filled with asphalt cement. Here, so if we looked at the first start, if we looked at this from a mass point of view, okay, we've got a aggregate with AC, and we got air voids. Obviously, this isn't the scale. So mass of air is 0. The mass of bitumen is pretty straightforward. If we know the percent of bitumen, okay, we know our total mass of mix. Remember, AC percent of total mix. If we take 5% times 1260, whatever it was, we could figure out our mass of bitumen. And MT, the total mix, is basically just bitumen, AC plus aggregate. Okay? And then the stone would be percent stone times the total mix, mass of total mix. So mass is pretty straightforward. Mass is pretty straightforward. Now, we're going to be talking about asphalt absorbed. Remember, absorption is by mass of aggregate. Okay, it's the aggregate that absorbs the AC, it's not the mix. You've designed the mix based on total mass of mix, okay? But the absorption is going to be dependent on the aggregate. How much is the aggregate going to absorb? So it's a function of A. It's a function of aggregate. Stone. PBA is the percent of absorbed asphalt by mass of aggregate. Remember that. Again, your formula here. I don't memorize these formulas. You keep working with them eventually, you'll stick in your head, but that's where you have your schematic plus formula sheet. Now here's the effective asphalt content. So this is a little bit different now. Okay, it's based on mass of total mix. The effective, okay, absorption of bitumen is based on aggregate. The effective percent of bitumen is based on total mix. Don't make that mistake. The effective asphalt content is the total asphalt content minus the percent lost to absorption. So you can see here, this is your total, 5%. If you had, say, 0.8% asphalt absorption, this would say 0.8, so this would be 0.008. So this would be 5 minus 0.008 gives you whatever, times the stone, would give you the X, okay? Okay, we've done a few things here now. We're going to look at some of these volumetrics. We're going to go through an example, actually. Just kind of give you the background and give you some definitions. Each one of these properties is important, and we'll look at it here shortly as to what some of them are. Okay, if you've got an asphalt mix, it's made up of air, you've got asphalt or bitumen, It's got a specific gravity of 1.015. And the percent bitumen, AC is 5% by total mix. And you know that of this AC, there's going to be some absorbed asphalt. So your aggregates come up to here, okay? This absorbed asphalt is in the aggregates. And you've got some aggregate. Remember when you guys did your blends, your combined aggregate blends, you had to determine the bulk specific gravity of the aggregate and the effective specific gravity of the blended aggregate. Okay, it's the aggregate that's in the mix, so it's a total aggregate. It was made up of the four aggregates: 16 millimeters, 6 crushed, natural sand, and VMA. It's made up of those. But now we got to treat it as one aggregate. So that's why we needed the weighted or the blended GSB and GSE. So they gave us examples here: 2.705, 2.73. If we look at volume on one side and mass on the other, and we're going to look at just 1 cubic centimeter. It's easy to work on one. You can work on whatever it is. Okay? And we did a bulk specific gravity on the mix, and we found out that we had 2.329. Okay? This is the bulk specific gravity. Okay, so let's start. We're going to start calculating some of these properties. Okay, what's the mass? What's the mass of the mix? Okay, we've got 1 cubic centimeter. We got a bulk specific gravity of 2.329, which is essentially density, and that's what they're saying. Volume times specific gravity times the density, 1. 1 times 2.329 times 1. Specific gravity is 1. So our mass actually is 2.329. Okay. Any questions so far? Pretty straightforward. Okay, so we know we've got a mix. 1 cubic centimeter weighs 2.329 total, MT. MT or MM. You can use MT, M for total or M for mix. Now we can break it out even further. How much of it is bitumen? How much of it is aggregate? Well, we know the percent mix. We know the percent AC. We know the specific gravity of the AC. So we can determine that the mass of bitumen is 0.116 grams. Subtract that, gives you 2.213. You can also calculate it. 95 times 2.329 gives you the same thing. But if you know the total mass of the mix and you know the mass of the bitumen, you calculate the aggregates or vice versa. So now we've calculated the amount of bitumen we have, and we also calculated the amount of stone we have. Now we're going to look at some volumes. We've got the two masses, and that's essentially all we can do on the mass side because the air doesn't weigh anything, so it's 0. So now let's look at the volume. Well, we know that the mass of stone is 2.213. So what would be the bulk of it? The total stone. Okay, we've got a GSB of 2.705, that's specific gravity, times the density of water, gives us volume. The mass divided by volume gives us the volume of the aggregate, the bulk volume, 0.810, okay? Yeah. The effective specific gravity, 2.731 of the aggregate. The mass, 2.213. Okay? The mass of aggregate doesn't change. The volumes will change. The effective volume and the bulk volume of the stone will change, but it's still the same mass. So that's why you can see here for VSE and VSB, it's 2.213 divided by the effective specific gravity times the density of water, it gives you 0.810. Okay, and the bulk, I circled this by accident about 30 seconds ago. This is your bulk aggregate, sorry. Circling VSE when we were talking about VSB, okay? So here's your total aggregate. This is your bulk aggregate, 8.18. The effective volume is only the part, okay, less. 8.10. So now we know we've got the effective volume of aggregate, and we've got the bulk volume of the aggregate. And we know that the total volume is mass divided by G times specific gravity. Okay, so density is mass over volume, volume is mass over density. Okay, mass is density times volume. Those are your three basic functions, and you can just work out just about anything. Any questions? Now, we worked on the masses. Now we know we got some AC there. Let's figure out what's the volume of AC. Well, if we know it's mass, we know it's specific gravity, we can determine. Okay, we have 0.116 grams. Specific gravity is 1.015. So the volume of bitumen, total bitumen, okay, is 0.114. Total bitumen. That's how much you added into it. Some of that got absorbed by the aggregate. How much? Well, very easy. 0.818 minus 0.810. Remember, the effective aggregate is the aggregate that has no AC in it. So if you know the volumes, you can just subtract the two. So the volume of absorbed asphalt is 0.008. And you can see here that we've almost got total calculation here. We can actually calculate air voids now, right? We've got this volume, this is one air void volume. Okay. We had 0.008. We had a total of 116. Now, the volume of the effective bitumen. Total bitumen was 0.114. Of that, 0.008 got absorbed. That leaves us 1.06. Sorry, 0.106. And the volume of air voids is just 1 minus 0.810 plus 0.114 gives us 0.076. The volume of air voids. Typically, air voids is always given as a percent, but you can determine these as a percent. Because if you know the volume and you know the total volume of something, you can then determine what percent is it of. Straightforward so far? We all know that mass is the volume times specific gravity times specific gravity of water. Right? So we get mass is volume times density. We can now calculate the effective mass, okay, and the absorbed mass of the bitumen. We know their volumes, we can now calculate the masses here now. So we've got a volume of 0.106 effective times specific gravity of the AC times 1 gives us the mass, so 0.108. So we know now that of the 0.116, 0.108 is the voids filled with asphalt. That's the effective bitumen. Same thing. Subtract that, and we know that we're left with 0.008. We started with 0.116, 0.108 mass, go to the aggregates, the rest got absorbed. Air voids, 7.6% of 1. VMA, we know that VMA is the effective AC content plus the air voids. VMA, the voids filled with asphalt, okay? The air and the voids. So that's pretty straightforward. 0.106 plus 0.076 times 100 gives us 18.2% of total mix. VMA is percent of total mix. Air voids is percent of total mix. So now we've technically calculated everything we need to know. So we've summarized. You can now determine the voids filled with asphalt. Okay, 18.2% VMA, 0.106 is what's filling the voids. So we 106 divided by 0.182. Remember, voids filled with asphalt is a percent of VMA. So 0.106 divided by 0.182, 58.2%. And you can also calculate the effective AC content. Okay, 0.108 divided by 2.329 times 100 is 4.6. We started with 5%, but the effective is 4.6. Okay, so we can go through these calculations. I'm going to leave that up to you. The rest is pretty straightforward. I'm going to go over a couple of these things, these terms that we're talking about. VMA, what's the importance of it? What's the importance of air voids and so forth? So we can carry on and we can calculate. So now we've got everything summarized here. Any questions? When you do those assignment problems, you'll get a better understanding of it. Any questions so far? Okay, I'm going to put something else up here. Okay, this has been uploaded in Learn for You. This was taken from one of the US agencies, but I thought it's a good summary. It was a bigger document, but I just took out the key parts, and some of this is we just gone over. This leads up to the calculation of volumetrics. And whether you're designing by Marshall or you're designing by the SuperPay program, the analysis of a mix is essentially the same. You're looking at the volumetrics. You're looking at air voids. You're looking at VMA. You're looking at voids filled with AC. You're looking at the AC content and so forth. So you'll see here again, taken out of this article, they're using the same acronyms, GMM, GMB, GSB, and so forth. I want to go over some of the key issues here. We've seen this chart. Some of these are just flip-flop, but they're the same thing. The volumetric properties, and here we've looked at it. Air voids, binder, VMA, aggregates. Essentially, it's aggregates and VMA. Add the AC to it. It's aggregate, voids filled with asphalt, and air voids. These are the ASTRO tests to run them. Air voids. Why do we need air voids? Well, they are the small pockets of air in there, and it's to help give us a quality mix, the performance. If you don't have those air voids, you're not going to have a very stable mix. Appropriate air voids contribute to the stability of the hot mix asphalt and help the pavement withstand the combined action of traffic loads and just the environment. Got to give some wiggle room. The designated percent air voids allows for thermal expansion of the binder, and it contributes to a cushion for future compaction. When we do an AC mix, hot mix asphalt, we design it. We design certain air voids, but when we put them in the field, we're going to actually have more air voids. But we're banking on the fact that those air voids are going to reduce the subsequent traffic and loadings. Air voids are expressed as a percent of the bulk volume. And there's your formula again that we just looked over. So air voids, you got to have them. If you don't have them, your mix won't be stable. And a lot of times you'll see that. You may see that in a rutting aspect. Pavement, sometimes you'll see the rutting effect where the wheel loads have come up, and usually you'll see them at traffic lights or stop signs and so forth. Okay. Percent aggregate, the stone. Okay. expressed as a percentage of the total mass of the sample. When we're talking mass, it's fairly straightforward, eh? Okay. Voids and mineral aggregate. It's the volume, the interangular, if you want to call it, the volume between the aggregates. And it includes the air voids, and it also includes the effective binder content, VBE, okay? Effective binder volume, expressed as a percent of the total volume of the sample. So VMA is a percent of the sample. Voids filled with asphalt. It's between the aggregate particles of the compacted paving mixture filled with asphalt binder, expressed as a percent of the total volume of the sample. The VFA increases as the asphalt binder increases in the percent of the voids are filled, as the voids are filled, okay? The VFA increases as the asphalt binder content increases, as it is the percent of voids that are filled with asphalt, which doesn't include the absorbed asphalt, okay? And the effect of specific gravity. This is what's going to govern, or this is what we use to determine the amount of binder, okay, that's absorbed into the aggregates. Talking effective now. This is calculated value based on the specific gravity of the mixture, GMM, and the specific gravity of the asphalt binder, GB. The measurement includes the volume of the aggregate particle, plus the void that becomes filled with water during the soaking period, less those that are filled with AC. The effective specific gravity lies between the apparent and the bulk. So that answers your question in today's quiz about the apparent, the effective, and the bulk. The effective lies between the apparent and the bulk. So in other words, the apparent is greater than the bulk. Then the apparent, okay? Say that right? Yeah, you got a bulk, effective, and then apparent. Apparent has the smallest volume, so you're going to have the higher specific gravity. Percent of the absorbed asphalt binder. Total percent of the asphalt binder that is absorbed into the aggregate, expressed as a percentage of the mass of the aggregate, rather than as a percentage of the total mass of the mix. Okay? The AC content, total AC content, is based on total mix. The absorption is based on the aggregates, because that's what absorbs the asphalt, the aggregate. Percent of effective binder, PBE, percent binder, bitumen, whatever you want to call it, effective. PBE is the total asphalt binder content of a paving mixture minus the portion lost by absorption. It's expressed as a percentage of the mass, aggregate mass. It is the portion of the binder content that remains as a coating on the outside of the aggregate particles. This is the asphalt content that controls the performance of the mix. If you have too much of it, too little of it, it's going to affect your mix, because then it affects your air voids. Too much, we'll have less air voids. Too little, we'll have greater air voids. We're not worrying about dust proportion. Some do, but I'm not. So don't worry about the dust proportion. But this gives you just a little bit of a concept of the importance of these volumetric properties. And it's unfortunate that we don't have a physical lab, but we're going to look at, do the lab. We're going to look at a video that Ray uploaded. I want to go through it because he covers a little bit of each thing. I want to highlight some of them. And if Ray will join us this afternoon, I'm not sure if he's on us right now, but you can ad lib also. Ray, have you joined us? I'm not even sure if you did or not.
I'm here.
You're there. You got anything to add, Ray? I've been talking here like a mile a minute, but I haven't heard boo from you.
That's That's all right.
That's okay? Everything's
Yeah.
good?
Yeah, there are students here. They will practice their ARP presentation. So
Oh, they're
I'm back.
practicing in
Yeah.
the classroom upstairs.
Mm-hmm.
I come to think of it, you did that too, didn't you, when you were doing yours?
I'm sorry.
You were also practicing in our classroom when you were doing yours a couple of years ago, eh?
Yeah, I did, and you were my mentor.
Uh-oh. Okay, fair enough. Okay, well, this is essentially what I want to cover. The video we're going to cover is part of the lab, so it's now 2 o'clock, so we're actually kind of on schedule. So if there's any questions on this, let me know. If not, we'll take a 15-minute break. We'll come back here at 2:15, and then we'll carry on. I'll just leave everything on. I'll just stop the recording and but leave the WebEx alone so we can just come back and sit. Look at those uploads, the chart, schematic, and the formula sheet. The formula sheet, um, you're going to need that, and you're going to need your schematic when you're doing quizzes, when you're doing volume calculation problems, those 2 assignments or 1 assignment I put up there, various examples, there's various types. Keep in mind that the exercise that we've done for blended aggregate, percent of blended aggregate comes into play. Okay, when we have a percent of a certain aggregate, we have to know its individual specific gravity to determine the blended specific gravity, because it's the blended specific gravity of the aggregate that we use in the calculations, not the individuals. So that's why the whole exercise was there. We'll come back. We're going to look at the labs that you're going to be doing. You're going to be doing the bulk specific gravity of the briquettes. You're going to be doing the GMM, and you're going to be doing stability and flow. And in Ray's video, he touches upon all of that. And I put up the procedures for all of them. You'll also notice there's a procedure for compacting the briquettes. Okay, 8A, fabrication of Marshall briquettes. Read it, be familiar with it. You're going to watch Ray compact one, but there's no lab for it. Okay, lab 8, well, there is a lab, but not for this year. Your lab 8 that you're going to be submitting is going to be the bulk specific gravity, maximum theoretical specific gravity, and stability and flow calculations. You're going to write up one report. But we'll get into that. Come back in 15 minutes. Any questions so far? No? Good. Okay. Let's take a little bit of a break and see you at 2:15. Okay? Stop the recording here. Okay, I guess we can get started here. I'll put the recorder back on. Okay, we're going to be looking at the labs, and I'm going to quickly go through these, and then we're going to look at the video, and I want to highlight a few things in the video. Parts of the video we've already performed, the blends and the proportioning that you're submitting in today. Okay, I've loaded up the 3 procedures, 8A, 8B, 8C, and actually 8D, 4 procedures. This is the preparation of the Marshall briquettes. Typically, when we do this lab, you figure out your actual quantities of AC and aggregate and write it up. In this case, be familiar with the preparation, know how they're done. There's some key aspects in there, but you don't have to comment on the preparation of the briquettes in your lab report. If you look at when you're preparing them, and if you look at most ASTM standards, there's a minimum reporting. So this is the information that you would include in your report when you're fabricating them. Type of aggregate, the source, and the grading, or your blended grading. The type and time of curing. We put it here that due to lab time constraints, we did not perform this step. What this actually means is once you mix AC, your aggregate, Instead of compacting it right away, you would put it back in the oven at a designated temperature for a minimum of 2 hours. You're conditioning it. With aggregates that have absorptions up to 1.5%, 2%, you want to cure them. You want to give it time to absorb. If you don't, then your maximum theoretical specific gravity is going to be off. Because remember, the GMM, the absorption on it, the effective AC content, is based on the GMM and the GSE. So you want to make sure that it's properly absorbed. But when we were physically doing this lab, our labs are typically 2 hours long. So you would mix it, put it in the oven, minimum 2 hours, or your lab's over. So we always have problems with our GMM. And then we would have to manually calculate them instead of using the values that we would determine by test. Okay. And here you can see a typical mold. These are Marshall hammers. These are automatic. Has anyone worked in an asphalt lab or has done asphalt testing? Asphalt testing? Hot mix? Anybody? I know Ray has. Nope. Okay. Okay, so this is the procedures. And again, these are based on ASTM procedures. Okay. All specific gravity. Once you've compacted your briquettes, you're now going to do weight in air, weight in water, weight SSD. Just like the aggregates are done SSD, where you wipe the surface moisture off the aggregate, you would wipe the surface moisture off the briquettes. So you have a weight in air and the SSD weight in air, and then you have a submerged weight. This gives you the procedures, and again, the minimum criteria that your report should have. We're calculating specific gravities here to 3 decimal places. It's important because it can change your final answer considerably. The density of the briquettes. Okay, you want to determine the average density of the briquettes. If you know specific gravity, you can calculate the density. And in this example here, because you got to have water at 25 degrees Celsius, we know the density of water is 997.0. So then we have to determine our density based on the density of water. Instead of 1 or 1,000, is 997. So density is the bulk specific gravity that you're going to determine times 997 will give you density. Okay, so this is pretty straightforward. I'll look at it in the video. This is the maximum theoretical specific gravity. We're going to use those bowls. Okay, we're not actually doing it suspended in water. If you weigh a known measure to the calibration mark with water, and you also weigh it with the material in it, and then you weigh it with the material in it plus water to the calibration mark, that gives you the volume. Go through these procedures. Again, minimum report criteria. There's a separate sheet for this, and I uploaded the data. Again, each group, 1A, 1B, 1C, 1D has data. Fictitious data that I put together for you guys that you would typically do yourself. One for the bulk specific gravity, one for the GMM, and one for the stability. And we'll look at that right away. Okay, so these are the procedures. So if we go to here's an example. This is group 1A, and then there's one for 1B, 1C, and so forth. But you'll also realize that the percent AC is different. Group 1A, yours is 4. Group 1B, yours will be 4.5. Group 1C, yours will be 5. These are the various asphalt cement contents that you're mixing. Because it was a group effort, and we had 6 groups, each group would have an AC content to compact their briquettes at, to mix their maximum theoretical specific gravity at. Then all 6 groups in group 1 would use everybody else's data. Because to determine your job mix formula, you have to determine those properties that we reviewed earlier at 4%, 4.5%, 5%. Okay? So typically, if you're working in the industrial lab, you would do it all yourself. But because we don't have the luxury, we don't have the time, we're only restricted to 2-hour labs, each group had to use the other group's data. So you would provide your data, somebody else would provide their data, somebody else would provide their data. So for example, group 1A, your bulk specific gravity is based on an AC of 4%. 1B, yours will be 4.5. 1C, 5, and so forth. So this is pretty straightforward. Bulk specific gravity, you calculate it, get an average. MTD, maximum theoretical density, which is derived from your maximum theoretical specific gravity. Again, 2 plus your average. So that's pretty straightforward. Okay, so this is actually A and B, because you've got the bulk specific gravity. Okay, that's lab 8B. MTGS is 8C. And stability. Procedures for stability. We just follow the ASTM. I believe I've uploaded these. It's based on the 15. Some key points are highlighted. View those. And your form lab D. So again, you would do the stability and flow. In other words, you put the asphalt cement down here, you can see, put it in a collar, the braking head, and you'll see that one right the video. And you apply a load to it, and you measure the peak load at failure and the amount of deformation or flow. Flow is the amount of deformation. In other words, as you're putting that braking head on the side, okay, you're not doing compression. You take that cylinder, put it on the side, and you load it this way. And then you're going to measure the amount of deflection that AC flows from start to failure. Again, you would have to measure the thickness because there's corrections here, as you can see on the bottom. So I've given you sample thicknesses, fictitious ones. You have to extrapolate the correct one, okay? And again, only to 1 decimal place because that's all your chart is set up to 1 decimal place. So your stability is the corrected stability. And you essentially take your load times your correction factor, gives you the corrected stability. Read the procedures. You can calculate it here to the nearest Newton, but when you report your results, in summary, to the nearest 50 newtons, the nearest 50 newtons, don't give it to me to the nearest Newton or I'm going to deduct marks. Okay? You can calculate here to the nearest. And you can calculate your average here if you want to the nearest. But when you summarize your results, your letter format, give it to me to the nearest 50. That's what the standard states. Any questions so far? So again, it's to correct it to the nearest 50. You don't take the...
You're saying 50, like 50?
50, 50. Read the instructions, it'll tell you. Yeah, 50. Okay, so Pavel worked on paving brown. Okay. So you actually, Pavel, didn't do any asphalt testing specifically yourself? Okay. So this here again, there'll be 1A, 1B, 1C. There's a form for each group. Okay. Now you can see here, we have maximum load in pounds not applicable. In Car C, their equipment was set up where the flow was measured in millimeters, but the actual load for the stability was in pounds, and then the students had to convert to newtons. So that's why you see the NA. I just didn't want to take it out of the pre-printed forms. So that's why maximum load pounds, maximum load. And your net flow, does anybody know? Oh, your description of sample. Well, what are you designing for? Okay, I'll tell you right now. What are we designing the job mix formula for? City of Winnipeg's got 4 mixes. What are we designing for? Type 1A. What's our AC? What are we using for an AC? What's our type of AC? Remember, it's in the city specifications. Anybody know the penetration grade? Include that. Sample description. Okay. The aggregates came from where? But make sure that you tell me what type of AC you're using in the sample description. Various grades of AC. Okay, it's in the city spec. Any questions so far on the data sheets here? They're pretty straightforward. Calculations are, anybody know how to calculate net flow? How do you calculate net flow? Anybody? No. And when you're running the stability, remember you're loading your stability, you're loading the collar, putting a load on it. So as this is traveling, as the load is pushing down, right? I can measure the amount of deformation. So at the start of deformation, you would read your load, your proving ring or your LCD, linear displacement, whatever it's called, yeah. And then when it fails, you would read it again. If you could always start at 0, then you wouldn't have to subtract anything. But this is the start of load and the end of load. So to determine how much it travels or how much it deforms, how do you calculate? Anybody? Well, figure it out, guys. Thanks, Fabian. Anybody else? Flow reading at start, flow reading at maximum load. Come on, guys. Somebody else tell me. Maybe I'll just award the mark to Fabian then. Anybody else? Come on. How would you calculate it? Okay. Well, we'll move on then. Okay. Now, so these are the procedures. They're all uploaded. I'm going to switch to that video and we'll go through it. And I'm going to stop throughout the video just to point out some key areas. Okay, I got to switch to a different screen here, so I'm going to quit sharing this. And share. See if this is going to work. can't seem to get the link. Yeah, I'm going to try going through the WebEx. So give me a minute here. Maybe it'll load up easier that way. Actually, Ray, if you can actually load it up, you can share it too if it's easier for you, but I'll see if I can load it through the WebEx.
Okay, let me check 1 second.
You get it up before me, go ahead. Okay. Can everybody see this?
Okay, there you go.
I don't have the whole thing here though. Okay. Okay, so if everybody see this okay? So Ray here is put together a video and also with the help of Art and Carsey. So he's going over the mix design stages, and you'll notice it's a brief video, but you can stop and discuss more. And if you have any questions, by all means, maybe blurt it out. I'll try and keep a watch on the chat here, see what's happening here. But take it from here. And like I say, if you have any questions too, you can, I'll keep an eye on the chat or blurt it out and we'll stop the video and there. Okay, Ray, whenever you want, stop. Also, if you want, if there's something I've missed, and let me know and we can discuss it, okay?
Okay.
Okay, here goes, guys. Hey, Ray, you're saying it's choppy and you can't hear anything. How do we get this volume on here?
I don't know, there's no volume on my computer.
The volume on
We
your computer?
have problems like this in the past. Anytime they want to share a video on WebEx, we can't hear it.
Oh, boy.
Oh,
Well, I guess what we can, okay, you're saying 5 frames per second. Is it too fast?
I will
We
try.
can-
I will try
No,
mine.
usually it's 24, 26, 30, 60. It just like it looks like a cartoon movie, you know, like one. So it's annoying, really.
Oh, okay. Because Ray, you can try it on yours and see what happens.
Okay.
What we can do too is if we can go to still life, we can let the volume, we can add our comments too. I guess the other thing is when you guys can watch it on your own, you should be able to watch it on your own through Learn.
Mhm. Okay, where is it again?
you find it, Ray?
Okay, I'll try it again. 1 second.
Okay, yep. Sure. See, I went through the web ad. Okay, here we go. No volume, Ray.
Sorry?
No
No volume?
volume.
Yeah. Mhm.
I wonder if we can do this a little still life at a time, like let it run and then stop it and then we can talk. Let me try something here.
Okay.
I'll take over here. Let's see what I can do here. I know when you guys will, give me a minute. Maybe it's gotta be under movies and TV. Ah, so okay. Nobody see that yet? Okay, just give me a minute, boys, here. Come on. I had it a while ago. How come I don't have it now? Oh, here it is. Okay, can you guys see this?
Yes.
Just give me a minute. I'm gonna try something here. Wonder if we got a transcript marks when we're talking.
No volume.
So like, can you see this screen or is it gone past for you guys or, oh, this is unreal.
Click the arrow on the top right corner.
Top right corner?
Yeah, that one.
Yeah, you can see a bigger screen here now, right?
Yeah.
Okay, Ray, ad lib. And then if you want, you can let me know. I'll go to the next frame and stop it. So you may want to talk about the screen for a while here, Ray?
Okay, sure. Okay, so let me close the door. So for this video, I'll be showing one asphalt content, which is 4% AC. And then the rest will be from another group members. And then this mix design will be in specification for the City of Winnipeg CW 3410 R12 for Type 1A. That's the latest specification for from the City of Winnipeg. Okay, so the first step to do Marshall mix design will be the aggregate selection. Okay, so I think, yeah, okay. For aggregate selection, we'll be using 4 types of aggregates. The first one will be 16mm crushed limestone. Second one will be crushed limestone fines. Next is natural fine aggregate and sand. Okay.
And we've already done this, guys, so you can. Ray, here's an example.
So it's this determination portion. And there are 7 axes, combine them in order to meet the specification for the city of Winnipeg, which is yeah, it should be okay. Yeah, and for asphalt selection. So I think earlier for requiring one type of is 100 that 150
150, 200.
yeah, 100 penetration grade. Zero to 3, and then there will be a mixing temperature. Temperature. Those information should be provided by the supplier, and also there is a call sheet. The all that the viscosity to determine your mixing and compaction temperatures, and then after that you calculate the mass required for your asphalt content. So for this one, which is 4%, we'll be using 50 grams for total mix. Okay, so when you're done with your aggregate and your asphalt cement selection, then we can now prepare our sample. So the first step in preparing sample is batching.
Okay, Ray, can I
Yeah,
interrupt?
okay.
Okay. What do we have here? You can see the Ray summarizes specific gravity penetration, mixing temperatures and compaction temperatures. Typically, suppliers come up with what's called the viscosity chart, temperature viscosity chart. And they pick 2 areas, and we'll look at this chart. And they have one for every type of grade of asphalt. And when you have 2 viscosities joined, you can then pull off, based on Centerstoke values, you can then pull off the compaction temperature range and mixing temperature range. That's what we determine our mixing temperatures. It's based on a viscosity temperature chart. Here's a quick little formula to determine what amount of AC you have to add to your 1,200 grams of aggregate. Okay, because remember, it's 4% of total mix. So basically, it's the mass of AC divided by the mass of aggregate plus AC. It's not like AC over aggregate only, like a moisture content, total mix. So if you flip everything around, you can solve for AC. So you can see the aggregate here is 1,200 grams, AC's in grams, AC's in grams here. If you're mixing at 4% or 5% or 6%, you can solve for AC. So the amount of AC you're going to use is going to increase with the AC content increasing. So then Ray said he's going to switch into sample preparation. You showed a viscosity chart here somewhere, did you not, Ray?
I'm sorry?
Did you have an example of a viscosity chart?
I couldn't find the chart that you gave it to me
Okay.
last 2 years ago. So
I'll put one up later. Anyways, and then you can see how we pick the compaction temperature and mixing temperature. Okay. Okay, go ahead. Now you can talk about the batching.
okay, maybe you can go to the maybe 1 minute after. Where's my script?
This one here?
Okay, there you go. Yeah, that's good. Okay. So for batching, it's important to dry your sample or your aggregates first, completely 100% before batching, and then wait it until it cool down. Then For this mix design, I use 5 batches. So each batch will have to have 1,200 grams to complete one test using 1 asphalt content. And then after that, using your tabulation to calculate the mass of each aggregate and determine the mass per size fraction.
And remember, you guys, you figured it all out. Okay, this is what Ray's referring to. We just did this lab. You're going to be submitting it, okay?
Okay. And then using your sieve shaker, I use a big sieve shaker. I think if you haven't seen that one before, it should be the one beside the small sieve shaker inside the lab. And then separate the aggregates into desired size fraction. And after you separate them, then using your tabulation, you have to weigh each size fraction for each aggregate, then combine the 4 aggregates thereafter. So on the picture there in the video, 1 tray is per 1 aggregate. And then if you can see the aggregates have different sizes. And then after that, you combine them to get a representative sample or 1 batch. And then you have to repeat the steps to obtain 5 samples.
See, in here, if I may add, Ray, these are just a little bit that Ray shows you an example, but these are the test fractions. Remember, passing, retained on, passing, retained on. And you physically would take all your aggregate that was submitted by Maple Leaf and you'd sieve it. So you'd actually have bowls. You remember those great big bowls they have in E109? The same style here, but the great big ones they use for washing. We used to get those full. And each one of these is a test fraction. So we would all separate it because you got to draw. Remember, there's 6 groups. In group one, there were 6 groups, and group 2, making 5 samples or 4 samples of each. So you would need a fair amount. So you can see here that we have to sieve all the percent passing, 3/4, retained, 1/2 inch, and so forth. Or sorry, 12 millimeter, so forth. So you would separate each one of these 4 materials. So you can see there's a lot of material that we'd have sitting around. From there, then you go and you take out so many grams of this, so many grams of this, so many grams of that, throw it in the bag. So many grams of this, so many grams of that, throw it in that same bag. So many grams of this, so many grams of that, so many grams of that, throw it in the same bag. So you're basically making up these samples physically. Okay, go ahead, Ray.
Okay. So after you've done batching, then we are now ready to mix the aggregates with asphalt. Okay, so I think 1 minute after. Yeah. So what we did here before we mixed the aggregate with asphalt, we set the oven at mixing temperature, which is 150 degrees Celsius. And then we place the aggregates inside the oven and then use a thermometer just to check if you have reached your mixing temperature. And also, we also put the asphalt inside the oven to get your mixing temperature. It should be the same temperature, your aggregate and your asphalt. Then we used a stove, or we will be using a stove to maintain your mixing temperature. So when you're ready to mix, so that bowl is your mixing bowl.
You can see it's buttered. You want to make sure it's greased up from previous mixtures. It's like buttering a concrete mixer. If you don't have some mortar built into the mixer, you're going to lose air. Same thing with here. You want to make sure that this is well buttered, as we call it, greased up, so the metal bowl will not rob out of the mix.
Yeah, because you're losing, if it's not battered, you're losing asphalt and aggregates.
Yeah.
And then that aggregate is on the oven. Oh no, sorry, it's on the stove. And with that temperature, we are checking if we have reached the mixing temperature. So you weigh or you tare. Okay, so you tare the mixing bowl and then you confirm the weight of your aggregates. If it's 1200, then 40 grams of asphalt cement is enough. If it's not 1200 grams or more than 200 grams, then you have to recalculate or determine your asphalt cement.
You're going to use that same formula that we just showed you again. Remember, because you're mixing this aggregate, you're shooting for 1200, but I explained to test before. As you're drying it, you may get 1195, you may get 1205. So now you have to determine the actual dry hot mass. And then on that mass, you base 4% or 4.5%, 5%, whatever you're mixing at. So in other words, you got to get a true aggregate mass. And there's hot aggregate. So like Ray said, you tear the bowl, you dump the hot aggregate into it, then you record it. And that's what you're basing your AC content on.
Okay, so when you're done, then you will create a crate on the center.
Trying to find that.
Yeah, it should be somewhere there. Oh, there you go. Yeah, create a tier or crate on the center, and then carefully transfer the asphalt cement over the asphalt aggregates. So you have to be exactly, let's say 50 grams, you have to have 50 grams. And if you're over, you can use a paper towel or any paper to take out any excess asphalt cement.
If you can't take out, let's say you can't take out that AC, because let's say you're supposed to put in 50 and you put in 54, and you can't get it out, let's say. Don't worry about it. Now you're going to base your actual AC 54 grams divided by the massive aggregate plus 54 grams. So instead of getting 4%, let's say that's what it was. Maybe now you mixed it at 4.2. And that's what you would do. Your AC content now is 4.2, not 4. You got to have an actual. You're shooting for 4. You overfilled it. You underfilled it, whatever the case may be. Typically, you overfill it. But then if it's 4.2, then you base everything on 4.2. Okay? It's not a big deal. You're trying to batch at 4, 4.5, 5, 5.5, 6, 6.5. So you're batching at 4.2, 4.5, 5. So be it. It is what it is. Okay? But sometimes you can get that AC out if you have to grease it. Put a paper towel in it and soak it up.
Yeah. Okay. So after that, you transfer again over the oven, and then thoroughly mix the aggregate until it's coated. ASTM D6926 suggests mixing approximately 1 minute for a single batch.
If I may make a comment here, Ray, actually, everybody in the industry does this, but you're not supposed to. When you add the AC, you don't put it back on a hot plate. You put it back on your plywood here, and you mix for a minute. The hot plate should not be used as you're mixing your AC. That's why you got to move quickly. So you got about a minute, and in that 1 minute, you can coat those aggregates really quite well. You want to make sure that it's well coated. Obviously, the less AC you have, the more it's going to take a mixing to coat it because you got a smaller amount of AC. But I've noticed in here, Ray, but that's okay. Like I see a lot of labs doing that. You got to be careful because you could be driving that temperature up a lot higher than the mixing temperature.
Yeah, yeah. I mean, make sure that the power is not too strong, or I mean, not overheating your asphalt mixture. And then after you mixed, after hot mix asphalts are ready to go, John mentioned earlier, asphalt mixes have to be conditioned for 2 hours before compaction or before testing. So we set the oven again at 139 degrees Celsius, which is the compaction temperature, for 2 hours. Then after 2 hours, we are now ready to compact the asphalt aggregate. Sorry, the asphalt mixture. It should be 1 minute after. Can you fast forward? Sorry. Yeah. Okay, there you go. Okay, so that is the color, the base, and then the mold. We preheated those three inside the oven together with our asphalt mixes up to 139 degrees Celsius compaction temperature. And then when ready for compaction, you have to put non-absorbent disc before you place or before you transfer asphalt mixes, and then transfer asphalt mixes using that. And then after that, can you pass for a minute just to see the stabbing?
Yeah.
Oh, there
See,
you go.
sorry, this is the disc I overrode. These are filter discs. So this collar lifts off and there's a plate under here. So you put up, your mold is oiled, lightly coated with WD-40 so you can extrude it easier. You put the disc on it, put the bottom mold in. Ray put all the asphalt in it with Art, and now he's gonna spade it around it, trowel it to make sure you don't get any voids. Go ahead, Ray.
Okay. And then after you transfer your asphalt mixes, you have to stab your sample 15 times around the perimeter and then 10 times over the interior. And then smooth the surface to a lightly rounded shape and place another paper disc on the top. And then now we will now transfer the whole mold with the asphalt mixes into the pedestal. Yeah, there you
So
go. Okay.
this is the compaction pedestal for the hammer, and there's a big, you'll see there's a big wooden block on here, a hold-on device that fits on top and it holds it in place, because you're gonna put a hammer in here after and compact it. So again, you can see they're wearing gloves because everything is hot. There's one thing you gotta remember, you always gotta have gloves, because you'll burn yourself if you don't.
Yeah, it's 139 degrees Celsius. It's gonna be hot. Okay, and then based on the City of Winnipeg specification, we have to apply 75 blows on both sides using a Marshall hammer. So in this video, we shouldn't use.
Yeah, just let me back up here. Okay, so here you can see what has happened. There's a vertical device here that's bolted to the frame and it slips over the handle of the hammer. Now, it came with that from the manufacturer. Why? I don't know. But if you read ASTM, it specifically states you shall not have any type of structure guiding the vertical, holding the hammer in a vertical position. You're supposed to just hold it with your hand and move the hammer up and down. Why it comes from the manufacturer of that, I don't know. Whether that was MTO that influenced them, because a lot of them come from Toronto, or whether MI here in Winnipeg. But if it's a manual hammer, you are not supposed to have any external device holding the hammer in a vertical, upright, plumb configuration. You, as the operator, are supposed to do that. Now, what happens actually is you might tilt back and forth a little bit, and that's okay, because that's giving you your kneading action. And that's what you kind of need, not too much. You're trying to hold a hammer vertically, but do not use that sleeve on here. The video would show them putting it on, but they're not supposed to. Here, let me just see if I can back that up here. There it is there. So you can see that. He's going to take the hammer, he's going to slide the handle in there to hold it vertical. No, that's a no-no. Now he's bringing the hammer up and he's dropping it. Go ahead, Ray.
Okay, so you have to apply 75 blows on each side, and then after compaction, we have to remove the base plate and the paper disc, and then allow the specimen to cool down at room temperature. You can use electric fans for rapid cooling, and then after at least an hour or so, we will be removing the specimen by means of a jack.
What he did here is he compacted 75 blows on each side. That's heavy duty. That's the based on your easel, the number of traffic counts you have on your pavements is 75 blows per side. And this collar, you reverse it. And there's a little bit of a nipple here that holds the collar in place. Holds the mold in place. Once it's done, like Ray said, now you're gonna take these papers off. It's a lot easier to take off. Mix is hot. You don't want any paper on it because you're gonna be doing submerging after.
Okay.
See here, you're taking it off.
Mhm. So you have to take, yeah. Okay, so we are now ready to.
See, now he's finished. He's taking the
Yeah.
paper off. Now you just let it cool. So
Mhm.
you've got these briquettes compacted now. You would do 3 of them. And
Yeah.
then you would obviously take the average. Okay.
Mhm.
So now the next step is we want to determine the bulk specific gravity of our mix. So we can do that based on our briquettes. It's the mix we're working with. So now we can be able to determine the voids based on the compaction energy and based on the air voids and so forth.
Okay, so this is the test for maximum theoretical specific gravity of asphalt mix. So the first step is to calibrate your bowl. So to calibrate your bowl is just to use 25 degrees Celsius water, fill the bowl with water, and then can you pass forward for?
Yeah.
Yeah, and then use the lid. Yeah, there you go. Then you will cover the mold with the lid, and then using that water bottle, fill again with water, and make sure that the water is flowing from the hole, and then wipe it down.
So you want to
And
make sure that's totally filled, no airspace between the lid and the.
then after that, take the weight of the bowl and water.
See, mass of bowl, lid, and water. That's what Ray's doing here. Okay, that's full at 25 degrees.
And then now we are ready to weigh our asphalt mixes. So using the same bowl, it should be the same bowl and same lid. Throw out the water, and then has to be dry. And then the asphalt mixes has to be in room temperature. And while it is cooling down, you have to separate the fine asphalt mixes, and doesn't have to be more than 6 millimeter in size. And then you will transfer your asphalt mixes into the bowl, tear that bowl, and then transfer the asphalt mixes, and then take the weight of your asphalt mix. Okay, and then after that, place enough water just to cover your sample, at least 2 inches. Again, it should be 25 degrees Celsius of water. Okay. And
You want to
then,
make sure it's covered, yeah.
and then using the agitator machine, we will now take out the excess or the entrapped air using a vacuum pump.
And you guys did that in geotechnical materials 1 with the sand or the soil that Natalie was teaching you. Same principle, except we don't have a flask here, but we've got the sample buried with water and we're de-airing it. Okay, we want to make sure we get the trapped air out.
So yeah, just cover with the lid, and then start the vacuum. The vacuum reading should be about 27.5 plus or minus 2.5. And then once the manometer reaches 27.5 or about 25, then you start the agitator machine for 15 minutes. Plus or minus 2 minutes. And then after that, we will take it out from the agitator machine and bring it back to your table. And then we will fill again with water. Same procedure when we calibrate our mold.
Again, it's good to have some de-aired water that you're adding to it if you can, and then because you've de-aired this water with the sample, so this water that Ray's adding should be de-aired to make sure it's. Or you could actually do a second de-airing, put some more water in and de-air it, so then you have very minimal, but depends on time.
Yeah, just be careful when you're transferring water. Make sure that you're not adding any air. And then, yeah, same procedure. Make sure it's filled with water. And then after that, take the weight of your bowl, asphalt mixes, and then your water.
So here it is here, mass of bowl lid, mix in water at 25 degrees Celsius. So in other words, your bowl now has water right to the underside. It's got the sample in it. So you're doing water displacement again. Remember, here we just had bowl lid and water. Now we've got bowl lid, mix and water. So it's the same analogy of doing a specific gravity on fine grained soils.
Okay. And then now we are going to do the bulk specific gravity determination. So after compaction, we waited at least an hour or so and then removed the sample using a jackhammer. Then in here, we'll be using a water bath with 25 degree plus or minus 2 Celsius of water. Then we will now immerse the sample in the water bath. So the first step is to take the weight in air per briquette. These are now called briquettes. And then after that, get your timer ready.
So here it is, your bulk specific gravity. You got your dry mass in air. So say 3 briquettes, record them there, okay?
Okay, so get your timer ready for 4 minutes. Then immerse your briquettes inside or in the water bath. There should be like a basket hanging under the scale. So your timer starts right after you placed your briquettes. Then after 4 minutes, you will read the SSD in water. Should be somewhere there.
I just want to back up here a little bit.
Yeah.
Okay. It's the same thing as when we did aggregate. Remember, you took your aggregate, you did an SSD, then you took it and you put it in the basket underneath the scale. Well, we're not using aggregate, we're using the briquette. But again, you want to have your briquette conditioned in water for 4 minutes prior to that. Then also any air that is trapped on top, sometimes a bubble adheres to exterior voids. So you want to make sure that the water basically removes any air that's trapped on the surface. Okay, so put it in ahead of time. Now when it's in the water, all Ray's going to do is zero the scale, drop it into the basket. So now he's going to have his mass in water.
And then now remove the briquettes from the water bath and then wipe it with a towel to obtain your SSD in air. Should be about 30 seconds or a minute. And then record the mass in SSD in air.
So you can see here now. Obviously, these have to be higher than dry mass because it's SSD. Some of the voids are filled with water, be it on the surface. So this is your lowest one, okay? These are your SSD or mass in water. Really, it's mass in water. It's not SSD mass in water because you get your SSD mass after you get your mass in water, right? Pull it out, dry it, so there it is. Really, a dry mass in water has been conditioned. Pull it out after you weigh it, then you get your SSD mass.
And then you repeat the steps to the other briquettes. And then now we will perform the stability and flow. This one has to be performed after 24 hours compaction. We'll be using the same briquettes from specific gravity. Okay, so what we did is we conditioned our briquettes inside the oven with 60 degrees Celsius temperature for 120. Oh, sorry.
Go ahead, Ray.
Yeah, for 120 to 130 minutes.
Okay, Ray, can you also instead of using an oven,
okay,
when you run your stability test, you can also condition it in a water bath.
You can also use a water bath based on the availability. We have water bath in B109, but we don't have water bath in car seat. That's why we use the oven. If you're using water bath, it should be, again, 60 degrees Celsius and has to be in the water for 30 minutes,
30 to 40, yeah.
30 to 40 minutes. Okay.
So both those type of questions may come on a quiz, guys.
Yeah, I was a student. Make sure you remember those numbers, especially on the finals. And then
John,
Yes, sir.
is there another quiz or is it just the final now?
It's just on the final.
Okay.
okay, so that is the head, or hold that again, John.
It's called a
the
breaking head.
The breaking head, yeah. So that is the breaking head that we're going to be using to obtain your stability and flow. So after 120 minutes, we will now take out our sample from the oven and then put it in the breaking head. And then place it in the loading machine. So as you can see in the loading machine, we have a load cell and an LDS. So LDS will measure your flow, and then your load cell will measure your stability. So the unit for stability will be Newton, and then I use the unit of inches in LDS. Okay.
So here the LDS, if I may say, Ray, once he's got this collar, it's a split sitting on top of the mix here. He brings this down so it rests on these guide rods that come out of the sleeve. These are set up a little bit different here because some people use dial gauges. We have LDS devices here hooked up to a laptop, so it's pretty good. It's pretty easy to read, and a proving ring. Some people actually have we got a load cell. Some people actually still use a proving ring. Either way, you want to determine the load on here. So he's going to bring this up until it reaches here, just to it. And as soon as it takes load, he's going to start, the computer's going to start recording.
Okay, so when you're ready to, when your LDS and your load cell are zeroed or tiered, then you can start the machine. The testing will last for a few seconds.
So he's setting the LDS here.
Yeah.
He's making contact. So as soon as he throws it on, you can see this gap here. So this may travel for a while before, and this won't start reading yet. Once it makes contact, once it starts to move, then that's when your deformation is starting. So he's setting the speed here. Well, how fast are you loaded, Ray?
The loading rate should be about, okay, where is it?
Testing you.
Forget the loading rate. It should be set up, but yeah, I forgot the loading rate.
50 millimeters per second, right?
Okay. And then, start the machine, or start your P3 recording first, and then start the machine. Then after a minute or 30 seconds, stop the machine and then stop recording. And then you repeat the steps on the other two briquettes.
See here, you can see it's failing, and the machine will show that, eh? You'll see your load just drop off, obviously, because there's some stability in it. So it's like a compression strength cylinder, except opposite. It'll take a certain amount of load, but when it fails, your load is going to drop because there's no resistance. But this will keep traveling, so that's why you have to have an initial and final. Because as long as this top collar keeps moving, it's going to keep recording deformation. You don't want to record the deformation here once it's failed. You want to record it from start to fail. How much did it deform? How much did it travel? So that's why you'll find out when you're doing these calculations, flows sometimes when you plot them, they're all over the map. And it's pretty hard to sometimes get an accurate reading. But that's why you do 3 or 4 briquettes, three minimum, and then you will average them. Keep in mind, when you're going to be plotting these, you may find your graph, like I said, a little bit ambiguous, but there is a trend that will always develop. and then you're going to do your best fit. You're going to take some of your data that may be outliers. Now, I may have given you data that'll give you pretty good graphs because it's virtual, but when you do this in practice, and Ray's probably done mixed designs at H. Mano, your data doesn't always come out as nice as you want it. Is that correct, Ray?
Yes. Hmm.
This is what's called the stability and flow, and all this is a breaking edge. I do suggest you watch that video from start to finish on your own. That way, through Learn, you'll get your own video, you'll get your own audio, and there are a lot of videos out there on YouTube, but you got to be careful. Some of them are garbage, just like anything else. I'm going to try and find some of the other ones, but Ray put this one together and it's pretty good. It's very brief, but whether you do one briquette or three briquettes, it's repetition. Okay. This is essentially part of a mix design, and it takes some time. And like when Ray said, and he can agree with it, the data I gave you might turn out pretty good, but in a lot of practice, it's not. And that's where experience in asphalt technology and behavior and performance comes into play. Your testing can only be as accurate as it can be, but now you got to interpret the data.
Yeah. And there are also like new machines now that show stability and flow right after. But for this lab, we'll be using this.
Yeah. There's a lot, Hermie, I don't, does Hermie have a load cell, or are you guys using proving rings? I mean,
we have the load cell, but we are using the dial
the dial, proving
to
ring.
measure your flow. Yeah.
Yeah.
Hmm.
But I mean, as far as load, did you use a proving ring or a load cell?
A ring. Yeah.
Ring,
You're
yeah.
using a ring. Hmm.
Yeah, with a dial in it that measures the deformation of the proving ring, because your proving ring is also tension steel, and when you squash it, it takes load. So there's proving rings and there's load cells. Load cells are more newer technology. This is typically what an MP3 strain would. So you could actually plot stress versus strain. But what I gave you in your stability and flow lab is the peak load and the start and the end LDS reading. So you can now determine distance that it starts to travel and what the total distance of deformation is. Okay. So this was just taken as an example out of the P3.
Yeah, channel 1 is your stability, and then channel 3 is your flow.
And here, for example, is an example where the flow would turn out to be 9. Okay, maximum load was 10. Sample thickness. Now, in our this is an older chart. In our sheet, we have the correction value fitted in here in between. So for 63.4, you can see at 63.5, it's 1. But you got to extrapolate. Don't record 1. It may, when you're rounding off to 0.1, correction factors to 0.0 to 2 decimal places. Okay, your sample thickness is measured to 1 decimal place. Your correction factor, you extrapolate to 2 decimal places, because your chart here is in 2 decimal places. You don't have to go 3, round it off to 2. And then it's 10,100 times, say it's 1. Okay, and he's got here 10,100. Here it's 10,300 times 63.6. And again, he chose just 1. He's cheating here, see? 10,200. This is just an example, guys. Okay, so,
Round up.
okay, so extrapolating between it, no different than what we do. So this is your flow and stability. So like I said, one group will have 4%, one will have 4.5%, so forth. Now that I remember the sample description, okay, we said it's 150, 200 pen grade. The supplier for the AC, Maple Leaf Construction, donated it, but the AC is manufactured by Husky Energy out of Alberta. Okay, I think it's Husky Energy, yeah. So that's who the manufacturer of the AC cement is. Maple Leaf purchased it from Husky. They donated it to us just like they donated the aggregates. Okay. I apologize for the fact that we couldn't have this video going on, but again, if you have any questions about the video, give Ray a holler. Do watch it. How do you learn? You should have no problem because I can log in onto it. And you'll notice there the various tests, MTD, sorry, GMM, GMB, stability, and flow. The hammer is a manual hammer, manually operated. The reason I'm telling you that is, again, you got to check the requirements of those ASTM procedures. They'll sometimes mention what was used, what has to be mentioned. Any questions so far? Went a little longer than normal, but I wanted to cover the lab here. If there's any questions for the lab, again, let myself know, or Ray, I can help you. If there's no other questions, then we're done. So this lab will be due next week. Again, a letter report. We want to have these forms filled out. Again, you do not have to fill out a form by typing. If you print my form, calculations can be penciled in. It doesn't have to be typed in. Okay? Typically in a lab, you would never type that in. That would be handwritten. And it would be in pen. You would never use a pencil in a lab. And you would never have an erasure mark. If you make a mistake, you put a line through it. It's like a survey book. What happens if you erase in a survey book? You get full marks? Read this? Anybody? You get a big fat goose egg, right?
I guess that depends how good your eraser was.
Yeah, but I can usually tell if it's erased or not. Because sometimes the guy doesn't use the person doesn't use the same pencil. After the fact. No, these can be handwritten. Some of these may have PDF writers on your computer, and you just might find it just as easy to type it in. But think of this as data sheet you would never give to the client. This would be in your project folder. You would summarize it, and you would summarize the data in a spreadsheet, but you wouldn't have to give your client all these information. Yes, go ahead. Hello?
Sorry?
What's that, Ray?
No, I thought you were looking for.
Oh,
Yeah.
sorry, I hit the button and it started the.
Okay.
And let me just stop sharing this.
Okay.
So again, your data sheet is something, you're submitting it to me as an attachment because I want to see your calculations. I want to see what you did. But think about going to a report. Why would you give that to a client? He wouldn't understand it anyways. He wouldn't know what initial flow start is, final flow start. That is things that goes into your project working file. You send the report to a client, you would summarize that. You can either summarize that in the body of a report, you can summarize it on a spreadsheet, summarize the data. Okay, so the data sheets, if you want to pencil your numbers in, by all means, that's not a problem. Okay. Any other questions? We went through this a little bit in the areas where it was quick, but again, we're pressed for time. I got all the time in the afternoon. That doesn't bother me. I just don't know what your schedule is. Is there any questions on these labs? No? Okay. Done. Have a good evening.
Hey, bye, John.
See you, right?